All right, welcome. We are going to be talking about section 4.3, but to start, we're going to do some warm-ups that go with 4.2 today. So you're going to do these first. There's 4 examples. You're going to do them like we're doing warm-ups. Instead of me sitting and waiting for you to do them, no, we're going to have you guys hit pause. And so when I'm done talking here, you're going to hit pause. You're going to try number 1 when you feel like you have an answer. Then you're going to hit play, and I'll go through that, and same with the other ones. So write this one down. Hit pause, and when you are ready to hear the solution, come back. All right, so this first one, we have x going to infinity. I mean, the first thing when you get these is that you need to check and see, can you just evaluate as is? So if I have 4 over, infinity cubed, that's 4 over a really, really big number, which can just be infinity. So that thing should go to 0, because 4 divided by a really, really big number is a small decimal. All right, here's the next one. Hit pause, try it, and when you're ready, come back. All right, so same start to the last one. We want to plug infinity in and see what we get before we automatically do a L'Hopital's or do any kind of factoring or anything. You'll also notice that you have a squared and a sign mix, so you're not going to be able to factor out and simplify or do any of that algebra stuff that we had. So in this case, we're going to try infinity. So infinity squared over 2 plus the sine of infinity. Okay, so infinity squared is just infinity. 2 is 2. Now, sine to infinity. You got to think a little conceptually here. Your sine goes like this. And as you go to infinity, what happens is you are bouncing back and forth from 1 to -1. So really this equals plus or minus 1. Not an exact value, obviously, but it's either, the denominator is either going to be 3 or it's going to be infinity over 1. Either way, infinity divided by 3 or by 1 would still go to infinity. So when you get some trig things in here, especially sines and cosines and possibly tangents, you got to be careful with the tangents, because remember, tangent has a lot of vertical asymptotes, and you've got a little different look to them. But sine and cosine, you sometimes need to get the graphical visual for yourself, and even going to negative infinity, you're still going to bounce back and forth between plus or minus 1 for your range there. All right, hit pause, try this one, and when you're ready, come back. Now this one, I could put a bunch of infinities in or negative infinities, but this would be one where I can do some factoring. So I'm not going to plug in yet. So negative infinity. I'm going to factor out my highest power, so x to the 27th. And I'd have 1 minus, this would become 2 over x to the 10th plus 19x to the 27th. Okay. Now when I evaluate my limit and I plug negative infinity in, I'd have negative infinity to the 27th times 1 minus 2 over, now negative infinity to the 10th will be a positive infinity, plus 19, and then this would be a negative infinity. Negative infinity to the 27th, it's odd power, so it's going to stay negative. Well, that just goes to 0. That just goes to 0. So I would just have negative infinity to the 27th, which is still negative infinity. Okay. The idea of factoring out here is that you get some terms to 0 out, because you're not sure what, this 19 and this 2x to the 17th, what effect those have on your visualization or your x to the 27th. Do they overpower, or do they, you're not sure. And so by factoring out that highest power, we can essentially 0 out, in this case, some of those now fractions. And so then it is an easier just negative infinity to the 27th. All right, go ahead, pause, try both of these, or if you need to, try one and then pause for the second one. You can go ahead. All right, let's start talking about A. We have x times secant of x, and you're going to 0. And I don't know where secant of x is. We have multiplication. We haven't done a whole lot with multiplication. So what I'm going to do is I'm going to convert this algebraically to be a fraction, because secant is just 1 over cosine of x. And I have x going to 0 still. Now notice in terms of work, and I did it on the other problems, but I didn't point it out directly, is that I still have this limit here because I have not evaluated the limit. In this last example, when I factored out, I had not evaluated the limit. So that limit notation is still there until you are actually evaluating. Okay, now I want to just check, maybe I can evaluate. So I'd have 0 over the cosine of 0. Okay, well, I need to know what the cosine of 0 is to know if maybe this is L'Hopital's, maybe this is not. So I draw my, radians of 0, my point is 0, 1, cosine is the first, so I have 0 over 1. Well, 0 divided by 1 is just 0, so that does end up to be 0. Okay, try B if you haven't yet, and then hit play and get your solution. All right, B, I'm going to start the exact same way, is that I have a multiplication. I want to get into that fraction format. Now I would be over sine x going to 0. Okay, you'll notice the nice part is I already have this picture here. So when I plug in 0, I would get sine of 0. So I would get 0 over 0. And 0 over 0 is one of those indeterminate forms. We cannot say the answer is any number or not or infinities. That's your indeterminate, which means that this is then going to go to a L'Hopital's rule. So I'm going to have limit as x goes to 0 still. The derivative of x is 1. Derivative of sine is, cosine. Okay, so now when I plug 0 in, I have 1 over the cosine of 0. We said the cosine of 0 was 1, so this thing evaluates to 1. Okay, be sure you only use L'Hopital's when you get that indeterminate form, 0 over 0 or infinity, a form of infinity over another form of infinity. Then you're going to be working with your L'Hopital's rule. Okay, let's hop into what 4.3 is. Now we're doing this first part with a video because these are all examples you have seen before. We're going to go through a few more definitions, and it's easier for you guys to kind of pause at your own writing pace here. And so that's why we're kind of starting this off with a video versus a live teaching of it. So 4.3, we're going to start getting some application problems here. As we're almost finishing derivatives, believe it or not. And so we're getting more application stuff. So optimization, like it says here, is just a fancy name for saying the largest and the smallest value, which we have already done multiple times in different sections, but we're going to kind of formalize and do a few more of them here. Okay, so some definitions that we have is that if f prime equals 0, then x is a stationary point, so derivative equals 0, stationary point. If either f prime of x equals 0 or f prime does not exist, that's that critical point of f. Okay, so those are some definitions that we have. A couple things you gotta be careful of is local versus global. So local max and mins may or may not be the global max and min. And so remember, global, usually we're talking about on an interval of some sort. It doesn't have to be, but usually it's, on this interval, what's your max value? And those are, when we're talking max and min values, those are y values that are the highest or the lowest on, this global area interval. All right, so those are things you have seen before. This is your new one. There are, I'll say 3.5, because one of them is a special case, but there are 3.5 theorems you need for your AP test. And this is your first one. It's called your EVT is the shortcut. It's called your extreme value theorem. Okay, and so this is very important. Put it in your notes, star it. You're going to need to know this definition. So if f is continuous on the closed interval from a to b, then f achieves a global and a global max and a global min on that interval. So extreme meaning max and mins. If you have an interval, it's continuous on the closed interval, and the closed interval is important. You can't have the ends be open. Then you have to have some type of max or min that occur on there. Okay. And with that, again, we've already technically done this. If it's continuous and it has that maximum value, they have to be at either critical points or the endpoints. So where your derivative equals 0 is undefined, or at those endpoints. And we've done this when we made that table. So like your endpoints were, -1 and 3, and you had a derivative that equaled 0 at 2, and then you plugged in those into your y and got your output. So you really have been doing everything we're talking about today already. We're just going to formalize it. All right, so let's preview what your problems are going to look like, and then we'll hop into do like 3 or so of them today. So extreme value theorem is what you are looking for is where your derivative equals 0 and where are your endpoints. The endpoints you will not always have when we have examples. Those might just kind of be inherited, like you're not going to have any negative numbers, so your endpoint would be 0 and up. Something like that. They're not always given as a direct, from -1 to 3, something like that. Okay, what Ms. Marshall and I are asking you in the AP board, for example, these are going to be the things that you must show. We realize you're going to have technology. You're going to have technology on your AP test. You're going to have technology when you take quizzes at home. These are the things that have to be shown. The first thing is that you take a derivative and what that is, and it has to be labeled. I've got a lot of people doing just random work all over the place. You need to be sure that you label. If your equation is called G, then you need G prime, and here's what that equation is. Okay? The next thing you need to do is set it equal to 0, and you have to write equals 0. That is showing that you understand that this can happen at where the derivative equals 0, and so that needs to be written. What's going to be changed now that we're going to have a little more examples versus in the past is that when you go to solve, a calculator can be used as a resource to solve where this equals 0. So you could graph it. You know, if it's a quadratic, you can use quadratic formula on there. You know, make sure that you are probably more than, you know, plus 3 decimals until the end. You're not really going to want to round until the very end. So write extra decimals, store them in your calculator, things like that until the very end. But you can use your calculator now to solve that equation equal to 0. Okay. When you solve it, then you do need to list out all of the zeros. Even if they're not going to be used, if they're out of that window or whatever, that's going to be the next part that eliminates those, but you do need to list all of the locations that f prime equals 0, even if they're out of those endpoints. Okay, so then 4 is that table of possibilities. What are the things that could happen? You know, make sure, you know, if there was a 0 that was -10 and this thing ends at 0, okay, well, don't put -10 in your table. You're just going to put the ones that fit in that range, okay? Make sure you plug them back into your original. You're not going to put them back in your derivative because you're going to get zeros for all these middle ones. You're plugging them back into your derivative. And again, as it says here, your calculator can now be used to do some of that simple algebra of, you know, plug a number in, get a decimal out, or whatever it is, okay? So you're going to have calculators during this process. And so this is the things that you have to have. You know, obviously the last one would be what's your answer. So 5, I guess I could put as answer, but you got to make sure you have all of these things shown, labeled, written out, multiple, you know, 3 decimals plus that as you work, 3 decimals for your answer, accurate, all those kind of things. All right, so let's do one here so you can kind of see what we're talking about. So let's find the maximum values of this function on 0 to 3. Okay, so going back, it said first you need the derivative. So f prime. So f prime would be 1/2 plus the cosine of x. Okay, it said set the derivative equal to 0. So great, 1/2 plus cosine of x. Okay, and solve. Now I'm going to solve it algebraically because we need more practice with trig. And so I'm going to do this algebraically, but on your homework and things, you are able to use your calculator here to do this. Okay, so I'm going to subtract my 1/2 over, and I want to know where the cosine of x equals -1/2. Okay, so cosine having an adjacent, so remember we have adjacent over hypotenuse then. So if my adjacent side is negative, that means I need to be going backwards. And so I would be either here, or I would be backward, you know, to the left, I should say. And I could have my hypotenuse being here or here. Okay, now again, we have to find all the zeros within, you know, the 2 pi here because we do have that range up there. So anyway, so this would be the square root of 3. This one would be the negative square root of 3. Either way, my reference angle is a 60-degree angle, which 60 degrees is pi over 3. The angle to get me to that location, though, would be 2 pi over 3. For this one, same thing. My reference angle is 60. It's pi over 3. But to get there, I would have 4 pi over 3 for that x value. So I'll say equals x. So I list out my first rotation of a radian there, what it would be. Okay, now I notice that my window, though, is 0 to 3. Okay, now just simple calculation and a little bit of mental math here. You know, pi is 3.14, so those kind of cancel each other. You have a little bit bigger, so this is 4 something, so that's too big. The only one that's going to fit on here is 2 pi over 3 in terms of what is between 0 and 3. Okay, and now here's where I'm going to use my calculator, and I'm going to plug back into f. So I know when I plug 0 in, I get 0. 2 pi over 3 is 1.913, and 3 is 1.641. Okay, I'm going to just use your calculator to do that. Now I go back to my question. Once you have your table, you got to write the answer. So it wants what's your max value. So my max value is 1.913, and my min value is 0. Okay, max and min values are y values. I know we've been marking lots of kids' quizzes and stuff the last couple, and said they write, you know, points or the x value. Max and min values are the y values that are the highest and the lowest on that interval. Those are your highest and lowest y values on that interval. Okay. All right, example 2. What point on the line y equals negative 2x plus 2 is closest to the origin? Okay. All right, so now we have an actual word problem because the last one was just straightforward, like find the max and min value. This is now an application. So let's talk through kind of what our steps are, and we've modeled this, but we want to just be as explicit as possible here. So the first thing you need to do is figure out what formula is described. Like, what are they going to be using? Is this a volume? Is this an area? Is this a Pythagorean theorem? What is the context that is going to be used? And with that, I'll say relationship between variables. So in this whole like drawing, you know, figuring out the formula, describing, there's going to be some variables that show up. And the other thing, and this 1, 2, 3 really should be all like step 1, is to draw a picture. And so sometimes drawing a picture might come first, then you see, oh, I have a right triangle and maybe it's trig, or I have a, you know, an area, so I can use the area of a box, something like that. And then these three all kind of get paired together to get you started. Once you get that stuff down on paper, then your next step is to do some type of substitution to get 2 variables only. And so when I say 2 variables, it's going to be in terms of only one. So, you know, area equals base times height. Okay, so that's 3 variables. Your area is going to stay, so I would need to substitute either for b or h to be in terms of each other, or they both become x's or something like that. So one of your variables is your lone variable. It's this side that you need to get in terms, so I'll say in terms of one variable for the one independent variable. Okay, so we're going to start modeling this and then kind of go from there. So if I'm talking about a line, so maybe I'm going to sketch myself a line. So 1, 2, I have a slope of -2. So here's my line. I want to be closest to the origin. Okay, I know the origin's right here. And I'm talking about closest from a line to a point. So let's see, like maybe we guess. We're like, oh, it's something here. So if I want to know the closest, that is kind of like saying a distance. And so I'm going to need the distance between some point on this line and my origin. So my formula described in this case is a distance formula. Okay, so I'm going to write down my distance formula. So x1 minus x2 squared, y1 minus y2 squared. So that's my distance formula. And then on there, I'm like, kind of step 2 there, what's the relationship between variables? Okay, well, so I've got a bunch of x's and y's. Sorry, jumping. And so I need some points. So I know one of my points is 0, 0, because it's at the origin. My other point is on the line, y equals -2x plus 2, but I don't know which coordinate it is. So I need a generic point. So a generic point would be like x, y. Okay, well, if I put x and y in here, I'm going to have 2 variables, 2 independent variables. So I'm going to substitute for y, and I think, okay, what does y equal in terms of x? Well, that thing is right here. So -2x plus 2. So now I've got point and point. They're in terms of one variable. I can substitute in, and so I'm going to change this to d equals to make life easier. So I would have, now I'm going to strategically put the x first, so I'd have x minus 0, so just x squared, and then -2x plus 2 minus 0, squared. All right, so here is my formula for the distance in this example between this line, the y equals negative 2x plus 2, and my origin 0, 0. Now this becomes the exact same problem we had before. I'm going to need to take this, take a derivative, set it equal to 0, all of those steps that we had before, because I am trying to find the closest, so I'm trying to minimize or optimize this thing. Okay? One kind of hint is before, so I'll say before, I'm going to say d dx. So before you take a derivative, you're going to want to simplify so that you don't have craziness happening. You know, if you did it this way, you would have like a double chain rule when you don't really need to have a double chain rule. So I'm going to simplify by foiling that out. So I'm going to have x squared, and then plus, it'd be 4x squared minus 8x plus 4. Will be that thing foiled out. I'm going to keep simplifying because I have two x squared terms. So I have 5x squared minus 8x plus 4. Okay. Notice I am still writing d equals because I have not taken a derivative. I'm just simplifying my original distance equation. Now I'm going to take a derivative and then set that thing equal to 0. So to start off my derivative, I've got a chain rule because I have a bunch of stuff to a half power. So I keep the bunch of stuff to a half power. Power out, power down. So negative 1/2, and then times the derivative of my inside, which would be 10x minus 8. Okay. All right, some algebra here, like I'm setting this equal to 0, and I've got like negative powers, I've got this half. I'm going to simplify a little bit, and I know when we did derivatives, you didn't have to all the time, but in this case, setting equal to 0, you do want to, because this solving is actually very easy. If you recognize that this half power would put it in the denominator, this 2 is also in the denominator, and so this thing is really simplified to this. And then if I'm equaling it to 0, okay, well I multiply the denominator over, so really I'm just saying 0 equals 10x minus 8. So, you know, add 8, divide by 10, so 4/5 is the x value that will minimize, in this case, that distance. Okay? Now, once you solve for x, just like before when we had these examples, you need to go back, which for it's a long way. The answer should be a point. So which point satisfies this? I just have an x value. So I have 4/5. Whoops, that's a 4. Sorry. 4/5. I'm going to plug that back into my line then. So negative 2 4/5 plus 2, which would come out to be 4/5 2/5. And again, you can use a calculator to do some of that, but this simple algebra, it honestly is easier than trying to grab a calculator and graph this, and where does it cross 0, and it's easier just to do some simplifying. All right, let's talk through, oops, what's the wrong way? One more here, and then we'll do more examples tomorrow here. So I want a rectangle under this line that is above my x-axis to the right of the y-axis, and I want the area of the largest rectangle that is formed. Okay. All right. So step 1, 2, and 3 were what's your formula. So I'm talking about area of a rectangle. So I know my formula is going to be area equals base times height. What are some variables? I'm going to wait on the variables till I do the picture because I want to graph. Whoops, let's make that straight. I want to graph this thing. Now, I'm not going to do it in a super good graph, but I'm going to make it big enough that I can write on it. So I know I'm up at 24, and then I've got a negative slope. And I'm just going to label this so that I know, what this thing is and where it comes from. Now, my rectangle has to be above this axis to the right of this one, and it has to be under. And so my rectangle is going to fall, oops, pretend that looks nice, something like that, and be on that axis. So here's my base, here's my height. Okay, so now I've got everything I need. I just need to do that substitution step, and oftentimes that is the challenge part of how do I substitute and what are all these things. And so hopefully by being explicit about what's my formula, what's my picture, what's my variables, And then looking at those and trying to connect those, it won't be super challenging. Plus, we'll do a lot of variety examples to help. So my base is right here. I know I'm going to need to be in terms of x because I'm on a graph. And so I just went over x, and so I can say my base is x. Okay, my height would be right here, so how high did I go? Remember, you know, your height, your rectangle could have been here as well, but your height is always defined by a y value, how high you go, and then y is always defined by that thing, so it's 24 minus 1.5x. So there's my area function in terms of x. So I'm in terms of one variable. I've got my a equals. So now I'm at the point where I can start this whole derivative process. Except if you keep it like this, you have to do a product rule. I want to try to avoid all that messiness, like your page 195 assignment where you had all these derivatives and things mixed and products and quotients and chains. I'm just going to distribute that x instead because that is way easier of a step. And so I still have a equals because I did not take a derivative. All I did was distribute. Now I'm ready to take a derivative because now it is a basic power rule. So 24 minus 3x. Okay, I set that equal to 0. 24 minus 3x. I solve, so I'd subtract 24. I'd divide by negative 3. So I would get x equals 8. Okay, last thing, I just go up and it says, what is the area? So it doesn't care the x, it wants to know my area. So I find my area formula, which is right here, and then I just put 8 in. So 24 times 8 minus 1.5 times 8 squared. You know, you can leave it like that. I think that's 96. You can, either way is fine. You don't have to simplify. Okay, so we are going to do more of these examples tomorrow live so that you guys can ask more questions. We just thought we've seen all of these 3 before, so we were like, let's try to get these to you a little directly, and you can watch them at your own pace. Your homework for tomorrow, or for today, excuse me, is back to page 231, back to limits. Okay, you'll get a homework assignment on 4.3 tomorrow when we go through more examples, but we wanted to give you some more practice with that limit stuff. So this is on Canvas as well. You know, go ahead and start trying that, and then if you have questions and things, we'll come back tomorrow to do those. Thanks for watching.